And I think my job now is to introduce Paul Michael of the Milwaukee School of Engineering and the chief or whatever. What's your title, Paul, for FPIC?
Director.
Director, thank you, of the Fluid Power Industrial Consortium. Paul, take it away.
Great. Welcome, everybody. Thank you for taking time out of your day and starting your Monday morning with a very interesting webinar. Next slide, please. Eric?
Uh,
Okay, yes. So this tells you a little bit about the FPIC. We're focused on market-ready technologies from the roadmap that can be implemented right away so that we can improve the performance and customer satisfaction of fluid power equipment. And everything that we're talking about is based on information that was collected through the NFPA road mapping process. Next slide, please. So I've got a couple things I want to notify you about that's going on at Milwaukee School of Engineering. Um, we are building an engineering innovation center right next to our old engineering building. And so I'm in my apartment today because my office is a construction site at the moment. But things are coming well. We've got the third floor up. And the idea is we want to do more integration of AI and engineering, and that's the driver for this innovation center. We need some better student collaboration areas, and then we're going to update our senior design areas as well so they can get more experiential learning opportunities and more hands-on opportunities learning about fluid power and all the other engineering technologies that we teach. There's 3,000 students at MSOE, and 75% of them are in an engineering program. Our largest program is mechanical engineering with over 650 students in the program. Next slide, please. All right. Hey, we've got some exciting news. We have initiated a fluid power graduate certificate program. And so in the fluid power graduate certificate program, if you are a senior at MSOE or a graduate student, or if you have an engineering degree or lots of experience in fluid power engineering, we offer a certificate program that involves 4 classes. They're evening classes, so you can do them after work to get the fluid power graduate certificate. And so we graduated our first student in May, and we've got 6 to 8 students in the program right now. So it's going quite well, and we're getting more interest in this area because it's quite interesting once they get experience. So we had like 20 people in our fluid power club. A lot of those students decided, hey, I'm really interested in fluid power graduate certificate. Next slide, please, Eric. For today's program, we'll be awarding continuing education units and professional development hours. If you'd like me to send you a certificate, just contact me at the email below, michael@msoe.edu, and I'll be happy to send that out to you. Paul asked if this is an online program. No, it's an in-person program with labs. So you get the hands-on experience with the graduate certificate program in fluid power. So that's part of the equation is that hands-on experience, experiential learning, which a lot of our students learn best when they're doing things with their hands. Next slide, please. So today's presentations, I'm really excited about our talks today. I'll let you in on something. I love big, well-engineered machines. Today, we're going to be talking about the Komatsu rotary blast hole drill. It's an amazing, big, beautiful machine. And we have 3 experts today to tell us about that machine. We have alumnus, FPI alumnus, John Gates. He's the principal he's a senior engineer in hydraulics. We have Cameron Raitt, who's a lead engineer in controls. And then finally, we have Shane Swagger, who's the senior principal engineer in automation. So we have 3 experts with the breadth of knowledge you need to understand how a highly integrated sensor system is enabling productivity, safety, and automation in the Komatsu rotary blast hole drill. John, please proceed.
All right, good morning, everyone. Just give us a second to get it. Perfect. All right, good morning, everyone. I want to thank you all for joining us this morning to listen in on all the exciting things we are doing here at Komatsu and have been developing for our rotary blast hole drills in regards to sensing technology and how it integrates with our hydraulic-driven functions. As Paul said, my name is John Gates. I'm a senior hydraulic engineer in the drill group here at Komatsu. Also presenting today will be Cameron Raitt, our lead controls engineer, and Shane Swager, our principal automation engineer. Our hope is that between the three of us, we'll be able to paint a clear overall picture of our solutions and where we're headed with sensing technology as we look into the future. We'll set aside some time at the end to answer any questions you may have. To better explain our application of sensing technology for blast hole drills, it's important to understand what a blast hole drill is, but first we need to understand what a surface mine is. Many people hear the word mining and they think of long, dark shafts where ore is loaded in carts and moved along tracks underground. This is kind of an antiquated description of what underground mining would be. When we use the term surface mining or open pit mining, we're talking about mineral deposits which are much closer to the surface, where the overburdened material is removed through a series of blasting, loading, hauling, and ultimately processing in order to extract minerals such as copper, iron, gold, and so forth. The picture you see here is the Rio Tinto Kennecott mine located in Salt Lake City, Utah. This is one of the largest surface mining operations in the world. They're primarily a copper mine, extracting roughly 140,000 tons of copper per year, although they do process metals such as gold and silver as byproducts as well. As I mentioned, the mining process involves blasting, loading, hauling, and processing. So the rotary blast hole drill is the very first step in that entire process. Pictured here is Komatsu's 320 XPC Ultra Class drill. It has a 1,000 horsepower electric prime mover powered from a 7,200 volt three-phase service. So this model is our largest blast hole drill, and it's used extensively in extremely hard rock applications like iron ore. In addition to the Ultra Class 320 XPC electric drill, we also offer several diesel-powered drill models. So pictured here is our ZR122, which is named for the 122,000 pounds of available drilling force. The tall structure you see sticking up into the air is called the mast on the drill. And on the mast is a hydraulically driven carriage on a rack and pinion drive for the vertical movement of drilling. The carriage also contains two hydraulic motors on a large gearbox transmission for rotation of the drill string. So together, this rotation and vertical movement are the motions used for drilling holes. There are additional auxiliary components mounted on the mast that are used for adding and removing drill pipe and drill bits as these consumable components wear out over time. Every motion on our ZR machines is hydraulically powered, whereas on our 320 XPC drill, we have both electric drive and hydraulic controlled functions. Our discussion today will be primarily focused on our ZR line, although there is some overlap with our electric machine. Today we'll be touching on many of the functions used when operating blast hole drills, but at the end of the day, their purpose is to drill out a series of holes in the ground called a pattern so that the blast crew can load the holes with explosives, set off the charge, fracture the rock, and ultimately load and process the material. These holes range in depth from about 50 feet all the way up to 280 feet deep. So as drill engineers, we can't help but include a short blasting video to illustrate this part of the mining process. So you can see the blast going off in the video right now. Hopefully this will give you a good understanding of what a blast hole drill is and the type of environment it operates in. So now I'm going to give a brief overview of some of the major components of the machine hydraulic system before Cameron goes into a little more depth on how we utilize the sensing technology to control various functions on the drill. I'm going to focus on our open loop or auxiliary circuit for today. This system on the drill controls all the functions that are not either drilling holes or propelling or tramming the machine from hole to hole. So at the heart of our open loop circuit, we have a 210 cc variable displacement axial piston pump. From this pump flows directed out to multiple valve manifolds that control actuators, which are mostly hydraulic cylinders, and these actuators perform various functions on the drill. The major valve manifolds we have on the drill include mast control, drill bit and drill pipe handling control, and leveling jack control manifolds. On each of these manifolds, we include a load sense pressure transducer to read the load pressure at the valve work ports when that valve is active. So we have two manifolds on the drill that are used to control functions like bit changing, pipe changing and storage, and breaking pipe joints. These are our drill bit and drill pipe handling control valve manifolds. Each of these manifolds has a master proportional valve and then multiple selector valves. Each selector valve turns on and off functions that require proportional control but do not need to run concurrently. This manifold design was chosen to simplify and cost reduce the manifold assembly, as only a single proportional valve is required, but we still maintain proportional control for several different functions. This manifold also includes a few additional independent on-off valve stations for functions that don't require proportional control. The mast control manifold has a proportional valve that directly controls the mast raise and lower hydraulic cylinders. Most of the time when our drill is working, the mast stays in its vertical orientation, but we do offer angle drilling options which require the mast to be tilted at an angle when drilling the hole pattern, and also when the drill is being moved off a pattern or propelling a longer distance or perhaps up a steep grade in the mine, we do lower the mast down to the horizontal orientation. The large hydraulic cylinders used to raise and lower the mast have integral counterbalance valves to prevent a runaway condition with the large overhung load of the mast when you're moving it up or down. A load sense pressure transducer is installed in the valve manifold and provides real-time feedback to our control system that's used to optimize the hydraulic pump setting and control when we're moving the mast. Just like the last manifolds I showed you, this manifold does also include a few independent on-off valve stations as well for functions that don't require proportional control, such as our mast pins, which lock our mast in place prior to beginning drilling. On our open loop pump, we have an integral proportional relief built in that's used to set the pump pressure based on feedback from the load sense pressure transducers that we have installed on each valve manifold. So the load is sensed by those pressure transducers installed in the load sense ports of the control valves, and then the pump relief is set using that value plus a margin pressure to match pump output to system requirement. This replaces a traditional load sense control where physical hoses would be routed from each valve manifold load sense ports and then back into the pump controller to set pump pressure. So we achieve the same result utilizing sensors, and we have the additional benefit of eliminating all those physical hoses and potential leak points around the machine. The last valve I'm going to touch on today is our leveling control valve. So we have 4 of these on the drill. There's 1 for each leveling jack, which are on the 4 corners of the drill. The leveling control valve is mounted directly to each leveling jack's hydraulic cylinder, and the manifold also contains counterbalance valves for controlled lowering of the drill and also locking the jack cylinder position when the level condition is achieved and the valve is off. A load sense pressure transducer is installed in the control valve manifold on each of these 4 leveling jacks. And similar to the mast valve, these sensors provide feedback used to optimize the pump setting and control when leveling the drill. Now, Cameron's going to go into a little more detail on that leveling process shortly and how that actually works. So that's a brief overview of the physical hydraulic system. And now I'm going to turn things over to Cameron Raitt, our lead controls engineer for drills here at Komatsu, and he's going to get into a little bit of how we actually use those sensors to control the hydraulics.
Right, thank you, John. So I actually have a factory automation background. So those who have done controls and automation for factory machines, they know just how exciting that is. So when I started at Komatsu 13 years ago, I was actually instantly drawn to the drill products just because they're unlike any other piece of mobile equipment that's out there. They're not just doing a repetitive motion over and over again. They're doing a series of actions through roughly 15 different subsystems with multiple variations of those actions. So actually drills were a very smooth transition for me from factory to mobile equipment. To touch base on some of those subsystems, prior to drilling a hole, we must be level to ensure our accurate hole trajectory, which is kind of what John was touching on in the hydraulics of the leveling system just a minute ago. So automatic leveling is standard on blast hole drills now. So we asked ourselves, how could we create a system that stands out as faster, safer, more reliable? So we started designing with the 4 independent proportional hydraulic jacks, which are the actuators of our system. And we selected a 2-axis can open inclinometer, which operates at typical accuracy of plus or minus 0.1 degrees. So, typical hole, 50 feet, we can be within inches of our target location, 50 feet down. So the accuracy really, really plays in there. And this is, of course, assuming that we've done an accurate calibration. This accuracy, along with the minimum sensor protection of IP67, which is a rating that we select for all our sensors on our drill, is what really drives our reliability. And there's also temperature ratings. -40 is our minimum as well for all sensors when we're selecting them. So speed, each of the 4 jacks has a linear transducer embedded within the cylinder housing to report cylinder extension with millimeter accuracy. So this allows us to advance our jacks full speed to the ground target position. And then just before we reach that position, we ramp down our speed, and then we begin monitoring our 3rd system, which is the demand and load side pressure transducers that John was mentioning in the hydraulics design. So the load pressure transducer, as John pointed out, allows us to vary our aux pump command based on the highest load pressure at any given time. So this increases our efficiency and it prevents chattering during certain retract scenarios. Our demand pressure transducer allows us to identify when each jack has actually contacted the ground. So with these measures, we were able to speed up our leveling by more than 20%. And from here, we decided, which direction we need to level. So this is the part of the routine where we're using the inclinometer, and we're applying a command in each axis that's proportional to the amount that we are off from our target angle. So that's where the proportional command really plays in for our leveling. When the machine is level in both axes and all 4 jacks are grounded, then we are considered level. So unfortunately, where there are hydraulics, there are hydraulic leaks. So that's where our demand pressure transducer comes in again to monitor the pressure feedback of each jack and trigger a regrounding if one of the jacks dips below our grounded threshold. So doing this step automatically saves quite a bit of time, considering that this would otherwise involve switching between machine modes, and then doing this step manually. So the above picture that you see here is an ideal level case for maximum stability. So all 4 jacks are down, and the machine tracks are in contact with the ground. When the machine is lifted off the ground, this is referred to as skyjacking, which is not desirable for the machine or for the operator. This leads to our last component, safety. So apart from what I mentioned with minimizing skyjacking through the cylinder feedback, we can also prevent hazardous manual operation of the system by utilizing all 3 of the mentioned sensors and bind the operator within a much tighter operating window from our critical angle anytime that the jacks are grounded. And we can then control which jacks can be extended or retracted based on what will improve their overall situation. So you can see in the diagram, they're forward biasing on that red dot. That means that the front jacks can only retract and the rear jacks can only extend, as that would improve the overall situation. So this allows them to drill on benches just below their critical angle, but level in a much tighter window to eliminate the potential hazard during skyjacking situations. I want to briefly touch on the next system, which is the mast raise lower. I know John touched on it a little bit earlier. So the mast itself is controlled with a pair of proportionally controlled hydraulic cylinders for raising and lowering, and then a pair of locking cylinders to lock the mast to the A-frame when it's raised. And then there's also a pair of locking and unlocking cylinders for angle struts. That's for optional angle drilling applications. And a feature that we've received great feedback on is our one-touch raise lower capability and one-touch angle drill. So at the heart of the control, once again, is our electronic load sense to step the pump into stages, which is the data diagrams that you see on the right there. We found this to be the most stable for our heavy-duty mast structure. Our proportional valve takes in a command map based on the same can open inclinometer just mounted to our mast. And that allows us to do a soft landing on the mast rest in case of lowering or triggering. In the case of lowering or triggering our locking pins, and in the case of raising. So the operator selects the target angle, and then with the press of a button, the struts are unlocked and the mast moves into that target position. And then the struts are locked in at that target angle. So this is where sensor accuracy and well-designed hydraulics are really important. We need a system that can be fast enough to go from raise to lower in under a minute, but accurate enough to land within a fraction of a degree tolerance to allow the angle struts to lock into place without binding up. And that goes for our mast raise as well. We don't want the pins prematurely extending during the raise process, and then they will bind up as well. So that's where accuracy and the hydraulics design really comes in. So we were actually able to do all that with our mass system, which I think is really cool.
Cameron, I'm sorry to interrupt. We have a question in the chat that I think this would be the right time to ask it. Do you face issues with sensor performance due to vibrations that may be generated and transmitted during the drilling operation? Any sensor failure issues due to high frequency vibrations?
Yes, definitely. We've run into that in the past. That's another component of sensor selection that is very important. Not just the temperature rating, but also the shock and vibration ratings as well. And then, the IP67 rating, which I touched on as well. So all these are like a minimum requirement anytime that we do a sensor selection. Actually, sometimes what we found is that the sensor itself can handle the shock and vibration during drilling, but it's actually the connector that faces issue quite a bit of the time. So that's where best routing practices come in, cable management, all that is essential for avoiding those issues, because the last thing you want is a sensor to take down the entire network. So those are all key points. So yeah, that's a great question. All right. Yeah, the next system I'll go through is the bit handling system. So as the machine is drilling through rock and ore, the bit itself wears out. So that's where the bit carousel comes into play. So that's what you see here. This is a 4-pot bit carousel with the ability to raise, lower, index. The whole table will index, and then each of the pots will thread and unthread. So basically, what the system is doing is it's taking a bit and shuttling it over to a bit basket and then dropping it into place. And then that bit basket, once it's unthreaded into the bit basket, it shuttles over the hole, and then the operator would thread on with the drill steel. So that's one way to eliminate live work on our machines, and combined with our deck winch, it avoids any heavy lifting. So it really makes the job a lot easier for our operators. They don't have to get out of the cab at all. As far as sensor accuracy, so the encoder that we have selected for our bit handling has a very precise indexing count. There's roughly 60 counts per degree, which is about 1/100th of a degree accuracy. So we have more than enough accuracy to properly place that bit. We have part presence sensing to know which pots are available and which pots have a bit in them. We can also track, based on where that bit is placed, the number of feet drilled on that bit as well. So all this leads into, and I don't want to steal Shane's thunder too much, more of our automated process of bit handling. Another one that is very similar is our pipe handling process. So drill pipe is another consumable, but even more so, our multi-pass drilling requires frequent pipe changeouts and overall extends the time it takes to drill. So multi-pass drilling is really, really a great application for like an automated pipe handling system. Once again, so on this picture here, it's just a 2-pot carousel, but we can have 6 pots for multi-pass drilling. And this has an even more precise indexing, about 1/1000th of a degree. So we have plenty of sensor capability there. With calibrated joint positions during the calibration process, that allows the operator to reach these positions very quickly. They extend a slide wrench over the hole to engage the pipe, and then they break that connection with a deck breakout wrench, which you can't quite see. It's just below the pipe carousel itself. And once the pipe is broken, then they unthread it, either add or remove that pipe into the carousel, and then swing that carousel back home. So there's a lot of controls happening with the bit and the pipe handling, which is very exciting. Once again, this eliminates live work because this can be done entirely in the cab. So the operator doesn't have to get out and eye up, where do things line up, and you can stay in the cab the whole time. And so this is just a sped up sequence of what exactly is happening. There you can see the pipe swung out of the pipe carousel swung out of the way. So this would be the adding pipe sequence itself. So the existing pipe is actually held into place with that slide wrench I was describing, and the pipe moves down to that location and threads on. And then they could continue drilling to their targeted depth. And then the slide wrench moves out of the way. So with all that, I think I covered kind of the basics of the subsystems themselves. With all that, I want to let Shane talk a little bit more about the automation of the machine.
Thanks, Cameron. Like was previously mentioned, my name is Shane Swiger. Been with Komatsu about 10 years, working in various different technology groups over the years, and now fully into drill automation. So go to the next slide, please, Cameron. So Cameron and John described the core hydraulic functions of the rotary blast hole drill. And so we can take that with their high level of sensors and automation of these subroutines and enhance with additional technologies to increase the level of automation and also to facilitate remote operation. So one of the core sensors that allows for that is high precision global navigation satellite system, HPGNSS. So probably heard more of GPS. So that's one constellation that feeds into that global system. So with that, we can now close the loop on the drill bit position. So we can calculate where that drill bit is in global space to within a few centimeters, and then have a control system that autonomously navigates the drill to position that bit over where the targeted position is for that hole. And then when we're drilling the hole, we can actually automatically drill to the designed elevation of that hole as well. So what that allows us to do, in addition to the functions that John and Cameron previously described, is now we can automate the entire drilling sequence. So navigating to the top of the hole, automatically leveling over the hole, and then automatically drilling that hole can be completely automated. This can be done with the operator in the cab, so they're still on board the drill, and at this point, they're more or less managing the execution of the pattern versus manually performing the drilling sequence. And we can add even further to that with different technologies like radars, lidars, a camera system and wireless communication to facilitate remote operation using those automated features as well. So there's kind of two main flavors of that remote operation, what we're calling a line of sight operation. So at that point, the operator can still directly control the drill with similar inputs like they would have in the cab with joysticks, keypads, etc. And they're meant to visibly be able to see the drill while they're controlling it. So that's more of the operator still kind of on site, maybe in a flexible trailer or running from the bed of a truck for some specific scenarios they can control the drill. And then higher level on top of that is non-line of sight teleoperation, where that operator may not even be at the site with the drill and they're allowed and able to directly control, or sorry, they are at that point are no longer directly controlling the drill, but they're more managing a fleet of drills from a remote control station using a mouse and keyboard as they switch between drills and basically queue up a series of holes for that drill to execute. Um, and as time goes on, further automations will probably be added as we continue to try to reduce the manual number of interactions that users have with the machine. So when you're running from a non-line of sight control scenario, you may have still user interactions with the machine to do pre-trip inspections, clean sensors, filling fluids, and as time goes on, there may be more drive to automate some of those functions as well. So in addition to increasing the level of automation and remote operation, some of these technologies also allow for the offboarding of the data generated by the drill, and that can be used to collect data to further enhance and simulate and test these automated features, but also do things like preventive maintenance and remote troubleshooting. And that also helps site and service personnel to have a better idea of what faults may be present on board the machine and come prepared with a troubleshooting plan, or even come prepared with the right spare parts because all that data is available to them before they even make it to the machine. Next slide, please, Cameron. So what does this mean for the customer? This means improved productivity on the drill. So that reduces their time to complete a pattern. It can also reduce the amount of fuel that's used to execute a pattern. The primary efficiencies gained there are in the autonomous navigation aspect and also from the automated drilling and leveling aspect. So as we start to get into the teleop portion, we can actually start to remove the operator from the machine. And so that helps reduce personnel to things like exposure to things like dust, vibration, noise, etc. We also gain some consistency, right? So if the machine is drilling and navigating autonomously, you get a more consistent operation. And that consistency is also helpful for the data generated, which goes and feeds back into the production process of the mine and then also into the planning process. So we do also see better accuracy, meaning accuracy where the hole is started and where the hole completes from an XYZ perspective. And so that will actually help in a few different ways. When the holes are drilled more accurately, you get better blasting, which means that the ore can be processed more efficiently. And then it also results in less cleanup time after the blast to prep the pad for the loading. So that's less time, less fuel, which translates into dollars. Some other benefits also, it allows new operators to become effective sooner. I think like a lot of industries, there's some issues with attracting and training new operators as some of the workforce starts to get closer to retirement age and things like that. This can also help with reduction in travel to remote sites. So some of these mine sites are very, very remote, very high altitude or in the middle of a desert, something like that. And so they'll have to fly operators and maintenance and other personnel in and out of site. And so if you're able to do a full remote teleoperation system, then you don't have to fly as many people in and out. So you can save money and time that way as well. And also that helps in attracting more talent too, so that way the operators can stay in the city where they live versus having to fly in and out on a rotating schedule. Um, I'll just close with kind of one of our taglines that materials extraction begins with drilling. So if you improve drilling, you improve your entire operation. Thanks.
Thank you, Shane. Well done. Thanks for doing such a good job explaining the benefits of automation and how it really improves safety and the quality of life for operators. I've got some questions. I got a question for Cameron on his presentation. He mentioned that there was some chattering in the retract mode uh, on the mast, and I'm wondering, I'm really interested in stick slip, and I'm wondering what exactly is causing this chattering when you're retracting the mast. Is it from the cylinder seal chattering, or what's going on with that, camera?
Yes, that was from the leveling actually.
Okay.
And specifically that was when we were skyjacked. And I think part of it was at the time a counterbalance valve sizing. I think we swapped those out to a different counterbalance valve and then it went away. But in the meantime, we did find that running it in a load sense configuration also helped. So yeah, hopefully that's a good enough answer for that one.
Yeah, that does help. So it's basically the stability of the counterbalance valve, and it was critical, if I understand you correctly, in terms of avoiding that chattering during retraction. That's
Correct.
cool.
Yep.
Cool. Yeah. Um, John, I got a question for you. Let's see. I was curious what kind of hydraulic motors you have on the drill system, and how that drill system works with the gearbox.
Are you looking for a brand of motor or what do
No,
you?
just is it an axial? Is it a radial? Is
Yeah,
it
it's they're axial piston motors on the drill for both the pull down and the rotary function. On the for the vertical motion that's on the rack and pinion, those are on like a self-contained gearbox, so it just mounts right into the end of that. For the rotary function, that's a Komatsu designed gearbox, so it's a whole gear system. The two motors plug into the top of it and they work together to drive the overall drill string.
wow, interesting. It's a long way to plumb the motor from the pump, isn't it?
Yes, it is a very long way. We have what we call our traveling hoses because you have to have hoses that move with the carriage as it goes up and down when you're drilling holes. And that's over 100 feet of line when you consider the going up the mast and then the loop of hoses that have to go to the carriage and move with it.
Wow. Does how do you manage latency in the system when you have, the modulus of the hose interact with the machine? How does that manage? Do you have a controls adaptation or adapt the controls in some way to account for changes in the diameter of the hose and the compressibility of the fluid, or is that something that does not pose a problem?
I would say it doesn't pose a problem. Maybe Cameron can chime in a little bit, but what we've found is that it's the actual drilling process is not so fine-tuned that's gonna make one a big deal either way.
Yeah,
Interesting.
I agree, John. Yeah, it hasn't really been much of a problem. I mean, we kind of tune in our systems, and they're all very once they're tuned in, they're very repetitive across machine to machine. So if there is any sort of difference, we haven't really noticed it.
Yeah, I'm sure there's decades of work that's gone into fine tuning that system. So,
Yeah, one thing we have found is when we first developed this system, we had sensors down closer to the pumps, and we had additional sensors up on the actual carriage. Um, and we did see obviously the pressure differential just because of those long lines. But what we found is it wasn't critical enough that we needed to keep sensors up on the carriage. Yeah, the
Hmm.
numbers were a little different, but the actual change in pressure as you operated your drill didn't change. So your sensors down at the pump level, easier to access, easier to troubleshoot. We kept those ones in, just knowing that the actual pressure up at the drill head is going to be a little bit lower just because of your line losses. But as far as control is concerned, that was good enough to have it down at the pumps rather than trying to include more sensors way up there and all the, cables running up there to control that too.
Cool. I like the way you explained the electronic load sensing. Thank you very much. That's good. Do we have any questions from the audience?
We do have one question in the chat. It's about magneto-restrictive or Hall effect linear sensors. Which one is better for handling vibrations?
I'm not sure which one might be better, but I believe what we're using is the magneto restrictive. Is that correct, Cameron?
Yeah, that's correct. Yeah, I'm not sure either. I
I
haven't
don't
seen any issues with that as far as vibration is concerned.
Yeah, I was just gonna say we haven't seen failures on the ones we use now, the magneto-restrictive design. So I would say they're good. I don't know if the other style would be equivalent, better, worse, because we haven't really tried it.
We also have a question about the typical service life of the drill bit.
That'll all depend on the material you're drilling.
Hmm.
So if you're in some extremely hard rock like iron ore, you may be changing your bit pretty regularly. If you're in soft rock, you may be working for a day or a couple days, maybe. I don't know. Cameron, you've done a little bit more into the bit changing side of things, so maybe you can get more accurate numbers. But that's my understanding is that for iron ore, you may be even changing after each hole, but for soft rock material, it'll last a while.
Yeah, and part of that is how the operators drill, not just with the material itself. Although, like you mentioned, John, the like iron ore up in the Iron Range in Minnesota, it takes them a good hour to drill a hole, whereas in copper and coal and softer materials, it's maybe 20 minutes
Hmm.
drill a hole. So it's quite a bit longer to drill. Also, so we have a auto drill routine that I didn't mention in the slides. So that is looking to optimize how that drilling happens. It puts specific force on the bit at all times, and it's able to handle multiple materials that you drill in. So if one of the settings in there is weight on bit, so ideally they put in what the bit itself is rated for. So if it's rated for 90,000 pounds, that's what the bit manufacturer recommends. They could push it up to 95 or 100,000 pounds, but they'll likely be changing their bits out sooner. So that's kind of where it's nice for the mines themselves to dictate what's more important. Do we want to save money on consumables, or do we want to um, push as fast as we can through the material to get these holes drilled out? So yeah, I think generally they're changing bits a few times per shift to average it out, but all these things play into it.
Right. And we just had another question come in electrical connectors were mentioned as problematic. Which styles give problems and which styles eliminate them?
So what we found, at least with our can open sensors, is that and M12s can be problematic, not in all scenarios, um, but M12s can cause some problems once in a while. They're more likely to suffer from the vibration and the strain that we mentioned earlier. Where we found tremendous amount of luck was with Deutsch connections. So we've moved a lot of things over to Deutsch. They're more robust for our application. Um, like I said, in the factory side of things, we didn't really have this issue. You're inside a factory. Things aren't, they're vibrating a little bit, but not nearly as much as on a blast hole drill, a piece of mobile equipment. So the other thing is that as those connections loosen up, you can get water ingress into the connection itself, and then that causes a whole slew of problems as well. So not always, but sometimes M12s can be problematic. And then Deutsch snaps right in and it's not coming out. It's sealed very nicely. So that's where we found a lot of relief from our issues.
Great. And the questions keep coming in. So the next one is, would you review how the controller prevents skyjacking?
Sure. So I guess generally speaking, like I mentioned with the jack cylinders themselves, um, we have the linear transducers within each cylinder, and we can generalize where ground is. So that's what I was kind of touching on with the speed aspect in my slide, is that we can approach that position very quickly, and then right before we hit that target position that's just above ground. Um, so what that does is then we're able to look at which is the low side of the machine, and we'll start extending those jacks. And generally speaking, what will happen is that the high side jacks, without extending, will touch ground at that point. So it'll actually tilt the machine to a point where the two jacks that are on the high side of the machine will touch ground, and then we can start the leveling process. And it works out very well because if you were to just extend all of your jacks to ground and then begin the leveling process, then you're more likely to run into a skyjacking or slightly elevated situation at the very least. So having those linear transducers in the cylinder is crucial for not only speeding it up, but preventing that skyjacking. And we can generalize
Interesting.
when there's a skyjacking situation just simply based on the linear transducers themselves. So hopefully that sums it up.
There's a request in the chat for a link to the Deutsch connector that you referred to. I don't know if somebody has the wherewithal or the time to provide that. And then I think this will have to be our last question, just in interest of time. There's a question about hydraulic hose versus electronic LS control. Any comments on choosing that route?
Yeah, like I mentioned in the presentation, one of the main things was just the elimination of extra lines coming back to the pump. As you can see, we have a lot of different things on this machine, a lot of different valve manifolds, a lot of things we need to control. There's already quite a bit of hydraulic routing on a drill. Even with the 122 drill, which we mostly talked about today, which is a pretty large machine, you run out of room very quickly on the machine trying to run lots and lots of hoses. So even though, load sense lines are small, trying to add in extra lines coming back from each valve, each manifold especially back into the pump area where it's already very congested, it just becomes very difficult to route. So using the electronic load sense that eliminates all those routes and it frees up area around the actual pump itself. So that's kind of the big benefit and the big reason why we want that way.
All right. Well, I think that's all the time we have for questions.
Very good. Thank you, gentlemen. I just want to express the gratitude from the audience and myself for sharing the decades of ingenuity that went into coming up with the design and automation systems for the Komatsu rotary drill systems. Very impressive. Very impressive. Next, I'm proud to introduce Professor Pawan Panwar. Pawan is a MSOE Fluid Power Institute alumni. He graduated with his PhD from the University of California, Merced, under Professor Ashley Martini, who's one of the leading minds in the field of tribology, the study of friction, lubrication, and wear of interacting surfaces. Pawan is the manager of tribology research at the Fluid Power Institute, which means that he runs a lot of projects and supervises the graduate students. And he is a wizard with sensors, data acquisition, and data processing. And today he's going to talk to you about how he's used sensor technology in both fluid health monitoring and pump health monitoring. And with that, Pawan, please kick it off.
Thanks, Paul. Thanks for the introduction. Let me share my screen. Let me see if you can see my screen. Paul, can you see my screen?
Cannot
Hello?
see it. Now I can.
Okay, good. Good morning, everyone. So currently at Fluid Power Institute of Milwaukee School of Engineering, we are working on various projects that focuses on accurate pump and fluid health forecasting through sensor technology. So today I'll present some of the findings from those studies. So let's start with the use of sensors to monitor contamination and degradation of hydraulic fluids. So as we know, hydraulic fluids degrade over time because of heat, catalyst, could be metal because of the metal surfaces and the wear in the machines, and also the presence of oxygen. The oil degrade produce varnish, which consists of partially soluble oxidation product, and this deposit can accumulate inside hydraulic system, which causes valve to stick and machine to fault, reduce heat exchanger efficiency, clog filters, and therefore reduce their life, increases maintenance cost and downtime, and therefore the objective of this study were to investigate varnish formation and their effect on the hydraulic on the heat exchanger performance. In addition to this, we also wanted to see if we could use the new oil conditioning sensors to detect varnish formation and also the precipitation of varnish. So we started with building a custom test rig using the Japanese Construction Machine Association standard PO45. In this test rig, if a fluid lasts for 500 hours, then it will last around 2000 hours in construction machines. So this test rig was run at an oil temperature of 80 degrees Celsius and a pressure of 5000 psi. We also injected a compressed air at the inlet of the pump so that we could oxidize the oil. We also use a copper catalyst. We place copper coil in the reservoir so that we can accelerate the degradation of the lubricant, and this test was performed for 1,000 hours. We used various sensors over the years. We used particle monitor. We performed the FTIR analysis both inline and using the benchtop. We also did infrared thermal imaging of this heat exchanger. We had fluid property sensors with that can measure wide range of properties, not just viscosity, density, and dielectric constant. They can also measure other properties, and we also used flow meter, which will be later used in the remaining useful life testing. So for this purpose, we perform the test on four different tests using 3 different types of lubricant of varying chemistry and varying oxidation tendency. Okay. So shown here are the reservoir and copper coil images before the test. So as you can see, all the reservoir and copper coil are clean before the test. And these are the copper coil and reservoir images after 1,000 hours of test. Okay, and we can see in test 1 with fluid A, there is not that much varnish, no varnish at all actually. In test 2, there might be a little bit, but it's negligible varnish. When we look at the test 3 with fluid C and test 4 with fluid C, we can see a lot of varnish deposition and the copper coil tarnished and converted into red or black because the degraded lubricant deposited on the copper coil surface. Now, when we look at the heat exchanger plate, it is important to know we use a special type of heat exchanger for this study. We use a plate and frame type of heat exchanger so that we could assemble and disassemble the heat exchanger before and after the test so that we can inspect the varnish deposition. So what we are doing is we are using the concept that as soon as the hot oil with varnish come in contact with the cold heat exchanger plate surfaces, the varnish will precipitate on the heat exchanger plates so that we could, at the end of the test, we could see which oil produced more varnish and had more precipitation on the heat exchanger plate. In addition to this, as I mentioned, we are also doing an IR imaging of the front of the heat exchanger plate so that we could see how the performance of the heat exchanger doing as the varnish deposits on the heat exchanger plates. So shown here are the new plates before the test. We use 10 plates. As you can see, all 10 are very clean, and this is the 10 plates after the test 1. It's almost same as the new plates. After test 2, there is some varnish deposition. And when we go to test 3, we can see lots of varnish deposition. The more in the beginning of the pump or beginning of the heat exchanger. So the heat exchanger, the flow start from 1 to 10, and we can see a lot more varnish deposition on the beginning of the plates compared to towards the end of the plates. When we look at the test 4, okay, we can see it has a lot more varnish compared to any other test. Okay, the reason is in all other tests we had 5 oil path. In the test 4 we had only 4 oil path, and because of that lower surface area we see more varnish deposition on the plates. Okay, so then when we look at the IR images of the heat exchanger plate, we can see something interesting. So as we start the test, oil warm-ups, okay, and you can see the belly on the heat exchanger plates. Okay, but what is interesting here, so this is showing the hot spot. Okay, this is where the oil enters and the water enters from the top and travel to the bottom, whereas the oil goes from bottom to top. Okay, so what is interesting to see that at 4,000 hours, the belly size start to drop. So what's happening? What's happening is that because of the varnish deposition around 400-500 hours, the heat exchanger is not able to absorb the heat from the oil to the transfer the heat from the oil to the plates or to the water, and therefore they will disappear after 400 and 500 hours. And this can also be validated when we look at the side glass. So we had a side glass. We were recording the video of the side glass so that we can see how the oil color is changing as the test progresses. And what we can see as the test progresses, the oil get darker and darker. But something interesting between 400 and 600 hours. Between 400 and 600 hours, the oil color intensity fluctuates, which is the point where the one is from the oil deposits precipitate on the heat exchanger plate, and therefore we see a demand in the heat exchanger, the water flow requirement to maintain a constant oil temperature of 80 degrees Celsius. Okay, and same thing we can see around 400 600 hours. The daily size decreases around between 400 and 600 hours. This also is proved when we conducted the chemical analysis on the sample collected at 100 hours every 100 hours. And so we did a benchtop testing, and what we found that the ZDDP, the zinc and phosphorus level drop around 400 and 600 hours. And when we look at the copper content in the lubricant, we can also see it maxed out around between 400 and 600 hours, because around between that time the copper coil is fully covered with the varnish. So this is interesting. The most of the additive deplete around 400 and 600 hour, and it deposit on the heat exchanger field. Therefore, the heat exchanger performance drop, and therefore it required more water to maintain a constant oil temperature. So we used a fluid property sensor. This is from TE Connectivity. Okay, we use this in all 4 tests. In the first 3 tests, it was installed before the heat exchanger. In 1 test, it was installed after the heat exchanger. We wanted to see if we can detect varnish earlier if we install the sensor in the colder line compared to the hotter line. Okay, so this is just showing the mean temperature at which those sensors were installed. And we can see all 3, the first 3 are installed around the same location, whereas the 4th one is installed after the test. Okay, and by looking at the picture, we can see this is the test 1. There is no varnish deposition. There is slightly, almost a negligible varnish deposition in test 2, lot more in test 2 and 3, and especially in test 4. We have a lot more varnish deposition because it was installed in a colder line, and therefore it also helped in early detection. Okay, so this sensor provides 5 different fluid properties, and we found that density and dielectric are the key parameter in detecting the onset of varnish formation. So as soon as we have fluid start to degrade at a higher rate, we can see that when at those points the density and dielectric is constant start to change with a higher rate. Recently, we installed a spectrolytic sensor system to our test rig, and this spectrolytic sensor system provide ISO code to monitor particle. In addition to this, it also provide acid number, the water content, and the kinetic viscosity at a chosen temperature. Okay. In addition to this, what separate this sensor system is that it can perform FTIR analysis in real time and provide us oxidation, and provide us how much oxidation we have compared to a fresh fluid. So it's a really good sensor, but the only thing is this is a very recent test where the fluid did not degrade over 1000 hours. So therefore we don't see any drastic changes in any of these fluid properties. We see that oxidation number is increasing as the test progresses, but nothing alarming here. So in addition to the hydraulic fluid, we also have an compressor oil edging test facility where we evaluate various compressor fluid, and in that test rig, we control the operating temperature around 115 degrees Celsius, okay, and maintain the demand, and so that we can compare two tests side by side. So in the same test rig, in this compressor test rig, we install the fluid property sensor that we found working really well. Okay, so this is just a circuit schematic of the compressor. We fully instrumented this so that we can evaluate how the fluid is doing and compare two tests side by side. So we had a fluid property sensor which worked really well in our accelerated oil aging test for hydraulic fluid. So we wanted to see how it does in the compressor testing. And what we found that in the PO45, the viscosity did not increase, but here in the compressor test, the viscosity was a key parameter. So this is showing the operating hours and the kinematic viscosity. And we have the density, dielectric constant, and resistance of the fluid. And what we see, in addition to the density and dielectric constant, as the oil ages, we also see a drastic increase in the viscosity. What we found that even though there was no varnish deposition in the compressor accelerated aging test, it is because of the different lubricant chemistry, and also there is a different degradation mechanism compared to the PO45. Therefore, whatever fluid property changes occur in the compressor test, it was purely because of the chemical changes in the test. So just to summarize, the test we built a test stand to study the effect of oil conditioning sensor in detecting the onset of varnish formation. And the test rig were able to consistently build the varnish, and therefore we were able to evaluate the effect of sensor. So what we found that the sensor properties were affected by the varnish formation and also the deposition on the sensor. The key parameter were the viscosity, density, and dielectric constant on detecting the onset of varnish formation. So this suggests that we could use this fluid property sensor to accurately forecast the end of the life of the fluid. So something interesting happened during this accelerated oil aging test, and that led to this second project where we are using sensor to forecast pump failure, so we can perform the maintenance on time to prevent downtime and costly downtime. So what we found that after 4,000 plus hours in our accelerated oil aging test, the pump, which was a vent axis pump, the flow rate dropped by 50%. Okay, so we almost destroyed that pump within 4,000 hours. So we wanted to see what happened, what actually caused the pump to fail within just 4,000 hours. So we took apart the pump, and what we found that there was abrasive wears on the valve plate. We found cavitation damages on the cylinder ports, and also inside the cylinder, inside the ports as well. We also found sliding wears and pittings on the pistons. So this catastrophic failure caused us a costly downtime, and also this kind of damages also causes collateral damages in the hydraulic machines, because the lubricating gaps are very small, and even a small amount of wear particle can destroy other component. So what is the solution? The solution is to predict remaining useful life of the pump so that we can enable just-in-time maintenance. So we first started with the data we had in hand from the accelerated oil aging test. So we started with oil temperature at the pump outlet. So we first remove the outlier noise from the data, and then we systematically generated more pump failure data. So we had only data from a single pump failure, and you cannot develop a machine learning or deep learning model using just a single set of data. So we needed more data. So what we did, we used machine learning to generate the synthetic data of 100 different pump failures. And then we developed the deep learning model using the convolutional neural network and long short-term memory. Okay, so what was the interesting thing when we compare those two models? Okay, so when we developed the model, what we did, we use 70% synthetic data to train the model, 10% data to optimize the hyperparameter of the neural network and LSTM model, and the rest of the 20% synthetic data plus the experimental data of the real pump were used to validate the model. And what we found that the convolutional neural network model achieved 95 or 92% accuracy, significantly outperformed the LSTM model. Okay. Results shows this, the convolutional neural network results shows that the pump failure, we can predict the pump failure approximately 300 hours before it occurs. So it means this model can allow around 300 hours before for us to perform the maintenance before it fails. Okay. What is the problem with this kind of model? Using the temperature to predict the remaining useful life. The problem is that the temperature response is slow because of the thermal mass. Okay, therefore it detects damages only after it occurs. Also, one thing is that when you use the temperature, it cannot isolate type of fault where the fault is in the machine, and also the temperature drift with operating conditions. So therefore, we had to use something else. So we did research and we saw that accelerometer have been used for decades to detect the fault in the machine. Okay, just to detect the fault. In the recent year, in the last 10-15 years, it's been used to predict the remaining useful life, but mostly for bearings, gearboxes, and turbo machinery. Especially the hydraulic pumps and motors are underestimated, especially because of two reasons. Because the wear is distributed between multiple sliding surfaces, and the hydraulic pumps operate at wide range of operating conditions. Therefore, when a system operates at wide range of operating conditions, the vibration signature also varies with those operating conditions. So when looking at the temperature sensor and the gap, we decided that we need to develop a operating point aware conditioning monitoring strategy that uses real-time vibrational analytics to forecast the pump failure and enable just-in-time maintenance so that we can avoid the costly downtime. So what we did, we modify our accelerated oil aging test, okay, so that we can perform an accelerated wear test. So this is our updated modified test rig, where we have now automated pressure control, and we installed two accelerometer, one a triaxial accelerometer and one single axis accelerometer. Okay, and then we perform the test at 25 different test conditions at 80 degrees Celsius. The speed varied from 500 to 1700 RPM, whereas the pressure varies from 2000 to 5000 psi. So these are the operating envelope in which we conducted the test. What we did to accelerate the pump wear, we put ISO dust. So we put ISO dust 17 different times, around 50 milligram per liter, or a very small dust, like even not even a pinch of dust. And then we allow 3 hours for dust to filter through the oil filter, and we collected a 5-second data using the accelerometer. Okay, we used a very high sampling rate for the accelerometer, and then we also had a particle counter. So when we look at the particle counter data over in this complete destruction of the pump, we can see each dust injection produce a sharp ISO cleanliness spike. The filter immediately cleans those spikes, the dust from the oil, until we put a next round of dust. Okay, so this gives us 17 clean and repeatable behavior steps, going from R0 to R17, where R0 is the new pump. Okay. Interesting thing to note here is after the 17th round, the dust, even though we did not add any more dust, the ISO 4406 4406 code continuously increased with the time, which suggests that the pump is now towards its end of life and it's now producing wear particle. So we, after the 17th round of dust addition and completely destroying the pump and reducing the efficiency, volumetric efficiency of the pump by 50%, we took apart the pump so that we could inspect. And what we found, that we had corrosion of the cylindrical ports. Okay, as you can see here, we found an abrasive wear on the valve plates, and this sliding wear and pitting on the cylinders or on the pistons of the pump. So we had total 187, more than 900 or around 900 raw data file with 5 seconds of vibration signal in each of them. Okay, so what we did, we splitted the data. We used the 70% of this data to train the machine learning model or deep learning model. And then we use another 15% to optimize the hyperparameter, and then rest 15% to test the model. So we use as a raw data or as an input to the model, we just provided the raw vibration signal without doing anything with them. Okay, so usually there are two types of model you can find. Usually you could provide the raw input directly from the sensor, or you calculate the engineering features such as mean of those vibration signal, standard deviation, those kind of thing, and you feed those to the model. But here we just provided the raw vibration signal to the convolutional neural network and trained it to predict few things: the pump shaft speed, the pump outlet pressure, the volumetric flow rate, and volumetric efficiency, and the remaining useful life. So shown here are the predicted. So y-axis shows the predicted parameter, and then x-axis shows the measured parameter. And we have the R-square value for 3 sets of data: training, validation, and the test set. And what we can see for the shaft speed, we have a very R-square value above the 99%. When we look at the pressure, we have the R-square value for the test parameter around 98%. And same is true for the volumetric flow rate. We have R-square value for the test data of around 98%. So then we were able to predict the speed and the flow rate. Now we can calculate the efficiency using the displacement of the pump. So we calculated the volumetric efficiency, and then converted the volumetric efficiency to remaining useful life. And we can see for the remaining useful life, we have an R-square value of 96%. Okay. So shown here are the volumetric efficiency and remaining useful life as a function of the wear round. So we put the dust 17 different times. Okay. So if you can see, when the pump was new, the efficiency was varying between 90 and 100. It's because we are operating the pump at a wide range of operating envelope. Okay, so and because of that, we have fluctuation. But those fluctuation is captured by the model. Okay, so when the pump was new and after the 17th round, the efficiency varies between 75% to 50%. So for some operating conditions, pump is already dead. It reached an end of life. For some, it is still good. Means if you are operating at those conditions, you can still run your pump for a few hours. So here we look at the remaining useful life. Again, we can see the true, which is measured versus the predicted, and we can see the model work really well. And when we look at the mean of the true and predicted, both are closely following each other, which suggests the model work really well. As a function of operating condition, we are able to predict both volumetric efficiency and the remaining useful life. So we use one sensor to predict 5 different parameters. So we wanted to see, since we use 2 accelerometer, we wanted to see, can we just work with a single axis or do we need a triaxial? And the R square value across all 5 parameters, the predicted parameters, when we look at the R square value for x-axis accelerometer data, y-axis z-axis, and then z-axis accelerometer data from a single axis accelerometer, we can see that the triaxial outperform all the single axis prediction, which suggests that we need a triaxial accelerometer in order to accurately predict both kinematic targets and the wear related targets. Okay. And we had for triaxial, we had R square value for all this parameter above 96%. Okay. So we wanted to see which axis is related to, like, better, which axis is more relevant in predicting the following parameters. And we found that the x-axis was, the x-axis vibration is a dominant parameter when it comes to the wear related targets, which is the volumetric efficiency and remaining useful life. When we look at the speed, pressure, and the flow rate, we can see the z-axis vibration signals are dominant. So just to summarize, we predicted speed, pressure, flow, efficiency, and remaining useful life at R square value above 95%, okay, with just 2 kilohertz data, and those were the raw data, and this is just a 5 seconds vibration signal. We did not use any engineering featured. We were accurately able to disentangle wear from the operating condition, as we saw that this test was not performed just at a single operating condition. It was performed at a wide range of operating conditions, and still we were able to disentangle the wear from the operating condition. Single axis accelerometer had significantly lower accuracy compared to triaxial, so we do need a triaxial, and the z-axis vibration dominated the kinematic targets, whereas the x-axis vibration dominated the wear-related targets in predicting. Okay, so the conclusion is that we could use the accelerometer to accurately predict the remaining useful life as a function of operating condition, okay, which can help us to forecast pump failure and also enable just-in-time maintenance. Going forward, we will also introduce different types of failures so that we could see if this model work can it predict different type of failures and also different failure mechanisms. Okay, so thank you for your attention, and before I end, I would like to thank my team at Fluid Power Institute, that include the director of Fluid Power Institute, Paul Michael, our full-time staff, Russ Stammer and William Tran, and our students who helped us, who run this test rig and collect the data for us. And at the end, I would like to thank our collaborators, Chevron and Donaldson, who help who work with us on this on the following projects. Thank you again for your attention. Please let me know if you have any question. Hello.
Yes, thank you, Pawan.
Thanks, Rick.
Paul, are you able to see the chat? Do you want to?
Sure. We've got a
Some
few
of the
questions
questions?
here for you, Pawan. One question is about the pressure. Let's see, it says, what is the, let's see, pressure control. I'm sorry, what is the typical pressure drop in the heat exchanger Pawan?
I think around 15 to 20 psi, not a lot. Maximum maybe 50 psi.
There's a question here about what mitigation measures are available to prevent scale formation on the heat exchangers. Now, scale usually talks about the formation of minerals from the water, but I think that we can speak to the deposits from the varnish.
Yeah, we did. So I just showed in the presentation the oil side. In the water side, we saw the scale deposits. Okay, and mostly we saw a lot more scale deposition when we had a lot more varnish formation. Okay, and especially the test 4, we had large amount of scale deposition. So use better oil, maybe that will ensure that heat exchanger is not overperforming or underperforming, or maybe yeah.
Thank you. There's another question here asking about the differences between synthetic and or biodegradable and mineral oils in terms of their varnish forming tendency. So in your study, you basically have shown the results for mineral oil-based hydraulic fluids. Is that right, Pawan?
Yes, yeah, we did not evaluate any biodegradable fluid or ester-based fluid yet. It's mostly the mineral based fluid, and we do not investigate into the chemistry of the fluid, and we just mostly get the fluid and perform the stage.
Can the spectrolytic system detect early varnish? Can you comment on its performance?
Yeah, so what we found when we compare the benchtop FTIR data with the spectrolytic oxidation prediction, they were in line. They had same trend and almost same oxidation number. Okay, so it means this can for sure help in detecting the onset of varnish formation. But we haven't had any fluid that had a lot of varnish formation with this sensor system. So we will have better answer once we have a fluid that degrade a lot more, because this fluid did not wear at all. It was very similar to the test 1 or 2.
Here we have another question for you, Pawan. The statement is very interesting work. Is pump life degradation as repeatable as the study assumes? Can the train model be tested to a new pump sample without dust addition and predict the remaining useful life accurately?
Yeah, so that's the plan. We have purchased few more pumps, so we plan to just try around 3 more pumps intentionally by cavitation, and in one case we will just wear the pump using cavitation, purely cavitation, and then in one pump we will simply use both cavitation plus the dust addition, and in the last pump we will not destroy it using any, like, artificially destroy it, and see how our model work in real time. So in the last test we will see how the model developed work without artificially destroying the pump.
There's another question here. A lot of people are commenting on your work being very interesting, Pawan.
Thank you.
Is the wear believed to be due to varnish formation?
I think it maybe negligible amount of wear due to varnish formation. It's mostly because of the cavitation. So you can see cavitation wear here. So the cavitation damages on the cylindrical port, and they were the large amount of wear was due to cavitation. Okay.
Mhm. Another question here is, did you use CFD simulations such as cavitation analysis instead of experimental testing to predict pump failure?
No, we have not done any CFD analysis. We wanted to do for the heat exchanger plate, but we have not done for the, yeah, we haven't done any CFD.
Great. So there's a question here finally about the presentation. Will the presentation webinar recording be available for another look? And yes, in the next week or so, we'll be posting a recording of Komatsu and MSOE presentations. And you'll receive a link from our association with that information. And with that, thank you, Eric, and thank you, guests. Appreciate your time.
Thank you, Paul. Thanks, Eric. Thanks, everyone.
Yes, thank you, Pawan. Fascinating work and lots of questions still coming in. So I think there's contact information that Pawan can share on one of his last slides there. I'm sure anybody with additional questions, you can reach out to him directly and get those answered. So yeah, we're up against time. That's going to wrap things up for our webinar today. Appreciate everybody's participation, and we do these on a quarterly basis, so look for a new one in early September. We'll be doing the next session. Thank you.
Thank you.
Thank you, everybody. Bye-bye.